let us consider a crystal of finite size, where I have atoms which are located only at the corners of the unit cell, and we will consider each atom to be a point scatterer. So, we are going to now look at the phenomena of scattering from a crystal of finite size. Here atoms only at the corners of a unit cell, and atoms are considered as point scatterers. Though the phenomena of scattering of X-rays from atoms occurs as a result of the electrons. So, strictly speaking, they are not point scatterers, but for all practical purposes we can do the analysis by assuming that they are point scatterers. So, if there is a, so I am considering this is my point scatterer, my incoming X-ray beam will get scattered in all directions in 3-dimensional space. Now, I am considering crystal of finite size. So, let us say that there are N1 atoms along A axis, N2 atoms along B axis, and N3 atoms along C axis. So, the total number of atoms are essentially N1 times N2 times N3. Now, let us consider just 2 point scatterers now. Let us take a point scatterer, I label this as A, and another point scatterer which I will label this as B, and remember all of these point scatterers are at the corners of a unit cell. Now, the AB vector, let me call it as the vector R. Now, I have an incoming X-ray beam of a specific wavelength, and the beam hits the 2 point scatterers. And let us take a particular scattering direction like this, and then there is some point far away, a point Q, where I place the detector. Now, again these 2 rays, call them as ray 1 and ray 2. Depending on the path difference, there could be constructive interference or destructive interference, and to find that out we have to find the path difference. So, let me just call this point A also as the origin. So, we will, with respect to this origin, we will do all the calculations. The distance of the point Q from the crystal is, let us say, capital R, and this R is much greater than the small r magnitude of the small r vector, which essentially means that we can assume that more or less the point Q is at equidistant from all the point scatterers, because this R is much larger than the size of the crystal. And we can also assume that ray 1 and ray 2 are parallel when they meet at point Q. Now, what is the path difference? Path difference between ray 1 and ray 2, let me call that again as delta. And in order to find that out, let me just do a small construction again. I drop a perpendicular from the point B onto ray 1, and I drop another perpendicular from point A onto ray 2, and let me label these points as C and D. So, the path difference delta is nothing but AC minus BD. Now, let me write down the equation for the incoming radiation. We will consider this as a plane wave equation in complex form. So, let me say consider ray 1, and I want to write down the wave at the point Q. So, at point Q, let me write down the wave equation. In complex form, and let me call this as y1. This is basically we are saying ray 1 at point Q. We are considering everything as at point Q, I do not need to write it again. So, this is due to ray 1, due to ray 2, which would have travelled a different distance as compared to ray 1. I can write by adding a path difference to this, which could be written as phi 0 upon r e to power I omega t plus, now I add as what is called as a phase difference, which is nothing but 2 pi by lambda times the path difference. So, delta is the path difference and 2 pi upon lambda times delta is called the phase difference. So, when the path difference is an integral multiple of lambda, which means that the phase difference is an integral multiple of 2 pi, which means the two waves are in phase, and when it is out of phase, the path difference is lambda upon 2 for example, then the two waves are completely out of phase. Now, we have to find delta. So, in order to find this, let me just add a few more things to this diagram. Let us say the incoming radiation, its direction can be defined by a unit vector, let me call it as S naught cap, and the scattered beam direction, its direction can be defined by another unit vector, simply S cap. So, S naught and S cap are the incident beam direction and scattered beam direction. And they are also unit vectors. So, now let me write down the path difference. So, path difference easily follows from here that delta we have already written here is AC minus BD. Now, AC, if you look at it, you take the dot product of the vector unit vector S and R. Then AC is simply nothing but the projection of the vector R on to ray 1. So, AC is simply equal to the dot product R dot S. Now, BD is simply R dot S naught, which could be written as R dot S minus S naught. Now, this S minus S naught, I can replace it by another vector and let me call that as capital S, and hence this could be written as R dot capital S vector, which we will call as a scattering vector. Before proceeding further, let me spend some time on the scattering vector S. Let me give it a geometrical interpretation. The geometrical interpretation, it could be, suppose this is now my vector S naught, this is my unit vector S. So, S naught is the incident beam, vector S denotes the scattered beam. Then very clearly the scattering vector S is the difference of these two vectors, or you can basically add up. So, this will turn out to be a vector in this direction, and if I bisect the angle made between the two unit vectors S and S naught by basically what I will call as an imaginary plane, then imaginary plane, this plane would be, or rather the vector S, the scattering vector S would be perpendicular to the imaginary plane. So, again we can assume, now if you notice this is basically my incoming radiation in the direction of S naught. It will make some angle theta here, it will make some angle theta here, and this angle will also be theta. So, it is as if there is a reflection taking place of X-rays from this imaginary plane. So, imaginary plane becomes a kind of a reflecting plane, but again there is no such process of reflection that occurs. Now, from this diagram I can also write the following, that the magnitude of the scattering vector S can, since S naught and a small s naught cap and S cap are unit vectors, the scattering vector magnitude would be 2 sin theta. We will take note of this and we will come back to this at a later stage. Now, what I want to do is find the resultant of, by adding up all the scattered rays which meet at the point Q from all the scattering centers in the crystal. So, resultant wave at point Q, and this is the result of adding from all scattering centers. And we already know that we have a total of N1 times N2 times N3 scattering centers. And this result I can basically, we can think of going back to this diagram. I have taken point A as the origin, From this origin A, I define all the scattering centers in the crystal, which will be given by some different R vectors. So, I need to basically do a summation over all the R vectors to get the resultant wave at the point Q, which essentially I am going to now do a summation of, take this equation and we do a summation over all the R vectors. So, phi 0 upon R, add up onto all the R vectors, e to power I omega t plus 2 pi upon lambda times the path difference. Now, instead of writing the path difference, I should write that the path difference is the dot product of R dot times the scattering vector. So, R dot S. Now, here we can slightly simplify it. We can take this omega t part out of the summation and I can write phi 0 upon R times e to power I omega t summing up over all the R vectors e to power I 2 pi upon lambda R dot S. Now, let us look at what is this vector R. Remember, we had scattering centers only at the corners of the unit cell. So, scattering center actually is the R vector is nothing but the lattice translation vector. And hence, this can be written as U A plus V B plus W C, where A, B, C are the unit cell vectors. So, U will vary from 0 to n1 minus 1, V will take a value from 0 to n2 minus 1, basically visiting all the scattering centers, and W will vary from 0 to n3 minus 1, where n1, n2, n3 are the scattering centers along the A axis, B axis and the C axis. And therefore, one can write the resultant wave at point Q in terms of 3 summations, one summation over U, second one over V and the third one over W. So, the resultant wave now I can write as phi 0 upon R e to power I omega t, and substituting for R now in this, I will end up first summing over U, let us say. So, U equals 0 to n1 minus 1, substituting for R into this, one will get e to power I 2 pi upon lambda U S dot A. The second summation would be over V, V equals 0 to n2 minus 1, e to power I 2 pi upon lambda V times the dot product S dot B, W equals 0 to n3 minus 1 e to power I 2 pi upon lambda W times S dot C. Now, let us just take a look at the first summation, because these summations are very similar. So, if we can solve for the first summation, we will be able to solve for the second and the third summations as well. If you look carefully on this, Let me kind of take this first summation and let me expand this. So, if I expand this for u is equal to 0, the first term will be 1, then for u is equal to 1, it will be e to power I 2 pi upon lambda s dot a. This is the second term. The third term would be e to power I 2 pi upon lambda s dot a, but this time u is equal to 2. So, I can write this as squared. So, this is u equals 0, this is u equals 1, this is u equals 2, and so on. The third term would be again inside the bracket the same term e to power I 2 pi upon lambda s dot a cubed, and so on till we come to the last term, which would be e to power I 2 pi upon lambda s dot a to power n 1 minus 1. So, if you look at this series, what kind of a series is this? Give it some thought before continuing the video. Well, what we have essentially, this is a geometric series. Now, a geometric series of the form, let us say the first term being T 0, the second term being T 0 f, the third term T 0 f square, and so on, the last term being T 0 f to power n minus 1 for a geometric series of n terms, where T 0 is the first term of the series and f is the common factor or the common ratio. So, this is how the geometric series is defined, and the summation of this geometric series is nothing but T 0 times 1 minus f to power n divided by 1 minus the common ratio f. This is the formula for the summation of the geometric series. Now, what is the common factor in our series out here? Well, this is clearly f, and T 0 is the first term, this is the first term. So, T 0 is equal to 1. Therefore, now I can write the summation u equals 0 to n 1 minus 1 e to power I 2 pi upon lambda times u s dot a. This summation can be written as T 0, which is 1, times 1 minus f, and f is e to power I 2 pi upon lambda s dot a n 1 divided by 1 minus e to power I 2 pi upon lambda S dot A. Let me kind of abbreviate this and write it in the following form. So, let me define a parameter psi 1, where psi 1 is defined as pi upon lambda S dot A. Hence, this could be written as 1 minus e to power I. Now, pi upon lambda S dot A is replaced by psi 1, and this n 1 can be brought inside, and there will be a factor of 2. So, I times 2 n 1 psi 1 upon 1 minus e to power I to psi 1. Now, it can be readily seen that this term and this summation term could be written as, let me write those terms, v equals 0 to n 2 minus 1 e to power I 2 pi upon lambda v times S dot B could be written as 1 minus e to power I 2 n 2, and in this case psi 2, where psi 2 is pi upon lambda S dot B divided by 1 minus e to power I to psi 2. Similarly, the last summation over W can be also expressed in a similar way, where let me define psi 3 as pi upon lambda S dot C, and this could be written as 1 minus e to power I to n 3 psi 3 upon 1 minus e to power I to psi 3. So, we have essentially derived an expression for the wave at point Q, the resultant wave at point Q, by adding up all the scattering centers n 1, n 2, n 3. And in the next lecture, we will work out what should be the intensity of that wave at point Q. Thank you.